Mr. Chairman, ladies and gentlemen, thank you for allowing me to address the conference virtually from Australia. Today I'll speak about increasing sugarcane productivity and environmental improvements in acid sulphate soils, a win-win system. We're going to trace today the study progress after the last 60 years from a non-productive entity of sugarcane, dairy and sugarcane farm to a very productive entity. How we dealt with acid sulphate soils by reducing the discharges of acidity, increasing soil carbon and soil pH. The move from a cultivated system to a green cane harvesting, no burning, and residue retention with an exponential increase and retention of carbon. A little about climate change and how we're dealing with it. This is where we are in the world, in Australia. We're in northern New South Wales, about 20 kilometres south of the Queensland border, 28 degrees south of the equator, and 153 degrees east. It's 106 hectares, half a metre above mean sea level. Average rainfall 1,600 millimetres, and from October last year we've had about 3 metres of rainfall, so it's been a challenging period for us. Marine mud overlain by 100 millimetres of peat, and 16 kilometres of drains reduced to 10. We found that the acid was coming from a wedge to the bottom of the drain and 5 metres into the field. Average production is 7,000 to 9,000 tonnes, and for every 100 tonnes of cane we produce 11.75 tonnes of sugar. This is, as you can see, it was a pretty sterile landscape back in 1962. Very little, only 40 acres, 16 acres of sugarcane, and the rest was dairy, very poor dairy country. By 1997, we had drained the property, reshaped the drains, and we were pumping, but not all that successfully. By the early 2000s, we had laser leveled the whole property. We had a better pumping system, and what we had then, it was, as the rain started, the pumps, automatic pumps started, took the water down to minus 60 centimetres below that natural drainage, and at the moment, because we've got really high tides, we're draining to minus 80 centimetres. This is a long-term equilibrium for sea level rise and temperature. The paleo data indicates that approximately 20 metres of sea level rise for every degree the Great Southern Ocean warms. So we've got a little bit of a problem. You can see that where we are now in 2100 plus a metre, that's a prediction. But on the long term, we'll see back in the last glacial maximum period, 20,000 years ago, where the temperature was only ambient temperature was only 9 for the world. The ocean was 120 metres lower, and now we're at zero. And if we were to go to 18 degrees, which we did last year for the globe, on a long-term basis, we end up with 75 metres of sea level rise. How we manage the risk from climate variability on the site. Longer dry periods, so we must conserve moisture in the dry, improve soil health, building soil carbon. Ingenuity in adapting harvester equipment, so we can actually harvest with water in the fields. Otherwise, we've had probably of the last 7 months, there's only been 20 days when we could actually work the fields. More intense rainfall, so we have to improve our drainage, plan spraying, planting and harvesting using forecasts. I might add there that the forecast this year showed that we were going to be very, very wet. The property is very low, so I chose not to plant cover crops, and if I had they would have been lost anyway. Sea level rise, monitoring the water table and pumping increased volumes of water. This gives you a bit of an idea how we this is about 2 meters of water there. There's a sugarcane crop underneath it. It did recover and went on to be a very productive crop. This gives you a bit of an idea. This is the where the pumping is, and this is where there's no pumping. This field here is just there. In the 2022 flood, we had water up to here, about 4 meters of water. We still harvested a crop, but it wasn't all that great. About 50% of a normal crop, which is still better than any other crop we can grow on these landscapes. This is the electric pump that starts on a mercury switch as soon as the water gets to minus 50 centimeters and shuts down at minus 60 centimeters. When to pump and when to just not bother about it. It's just too it's broken the levees, and so we shut everything down and wait till it goes off the levee banks and start again. These fields here are probably a 1 in 6 month event. This is the pumps going, and this is what happens when you harvest in the wet. At the moment, the dewatering pumps are pumping into the river about 4 million litres per hour. Based on recent rainfall events, we're increasing this to 8 million litres per hour. It'll give us a little bit more security. The reason for that is that we have for the first 7 days of waterlogging, there's very little decrease in production. It's pretty much a flat line. After that, this production is lost at 7 tonnes per hectare per day, and it's not real good. It's one of those things that we have to manage. Drainage is the major thing we have to deal with, getting the water off the fields as soon as possible. These are mounted up prior to planting. The cane is planted at natural ground level, and then the planter remounds over the top of it. And we've been able to increase. That was one of the big reasons we increased productivity. And there's quite a bit of residue still left there, and that helps build the carbon. This is the result of a 360-day study by a PhD student. She found that the sugarcane was taking of the ambient CO2 about 121 tonnes of carbon out of the atmosphere each year, and storing it in the landscape and in the sugar, which goes off and is revived. So what she was able to deduce from that was that after we discounted planting, harvesting, transport to the mill, crushing, etc., everything, we were still 9 tonnes positive. And a wetland, the alternate use for this land is wetland, and that would have captured 1.5 tonnes of carbon per hectare per year. This is a CH4 flux or methane, and the work showed that on 50% of days, or 54% a day, we're actually a methane sink. In flood time, there's or when there's the water pressure on top of the ground, it ends up emitting the methane. Once it's drained back down to the ground level, there's no more emitting of the methane. So these are some of the things we had to do to get a result. Every cultivation you do is burning off some of your organic carbon. Burning is some trial work we've done recently shows that if you don't change, and I'll speak about this more in a moment, if you don't reduce the don't change the carbon to nitrogen ratio on the residue, you're better off to burn. There's more carbon captured. The thought was that everything was going off as CO2, but if you leave residue on the ground with and don't treat it with change the carbon to nitrogen ratio, you end up with more CO2 going into the atmosphere. If this tractor with a rotary hoe had an animation on it, the flames would be similar to this over here, burning off the organic carbon. Building carbon in the soil. We've done a lot of different trials. One was with oats, and these oats were grown with 10 kilograms of urea, with just and they got most of their nitrogen from the breakdown of the residue in the soil, and sugarcane gets 40% of all its nitrogen from the breakdown of the organic matter. So no organic matter, it must come from a bag and put into the soil. So it's a win-win. This is one of our win-wins. This is changing the carbon to nitrogen ratio of the residue, and we spray with 5 to 8 kilograms of urea per hectare, and what that does is changes that carbon to nitrogen ratio. The breakdown is more, well, instead of going back into the atmosphere as CO2, it's taken it activates the microbes that take it down into the soil, and we have an exponential increase in soil carbon. It was always a problem that after rainfall, the residue is fairly buoyant. It would lift up, float, and go and cover another crop and kill it. Well, that doesn't happen anymore. These are so we moved from a cultivated system where we cultivated the interspaces every up to 15, 20 times a year, burning off our carbon. We moved to a green cane harvesting, no burning, residue retention, and because we're wet and cold, we actually rake the top of the stool, let the sunlight in and the warmth, and then we fertilise with this stool splitter, which is got a compaction wheel now. That's been added, and there's very little. Well, we haven't been able to get a measurement of the loss of N. This is what the field looks like after it's been sprayed, fertilised, and raked. And we've also, about this time, we've sprayed it with residual chemicals, and we can walk away from that then for 12 to 14 weeks and just do a final spray at the end. As you can see, there's a fair amount of residue, probably on estimates about 15 tonnes per hectare. So that's every year, and we're building our carbon through that. This is to give you some indication that the residue is retaining moisture. This was during the drought of 2019, and these were the only fields that were cut without burning, and they've retained the moisture, as it looks very obvious. These are the latest soil tests, soil and carbon tests. It indicated that there was 14% organic matter by weight, and in the common conversion, 58% carbon content. That gives the soil carbon content 8.86, which is, and in the first slides I showed in the 1962 air photo, this was bare ground. There was the cattle went there but only to have a look around, looking for something to eat, and there was nothing there to eat. I was fortunate in 2016 to be the Carbon Farmer of the Year for Australia, and the prize was that they come to the farm, the 100 hectares, and did 80 carbon cores. With a standard error in the calculation, soil organic carbon standard plus or minus error, the whole farm measurement of C stocks, 17,478 tonnes at 30 centimetres, and at 1 metre it was 20,000 tonnes, around 77,000 tonnes in CO2 equivalents. In November 2024 we did another lot of tests, only 34, but that gave us an indication that we've increased again by another 25,000 tonnes in CO2 equivalents. The equation for measuring how much carbon is the 100 hectare site with an average 5.5 organic carbon in the top 30 centimetres and a bulk density of 1.33. That is 220 tonnes of C per hectare, or 80,000 tonnes of CO2 stored on the 100 hectare site. Reduced only when residue only has enough N to increase the soil organic carbon by 0.2% every 6 years without a change in the C to N ratio. And mine has had the study site has increased by 4% over 20 years. This is the macrofauna. This was when we started to convert to sugarcane. This land here had a pH of around about 2. It's got 50 tonnes of oxidised sulphuric acid per hectare in the landscape. So we had to design a system where we actually farmed over the top of the acid. Earthworms can't exist, I'm told, below 6 pH, and these birds are chasing earthworms. Yield decline solutions. Some of the problems we have are with weeds in particular. Sugarcane's a C4 grass, so any C4s that get in there are very hard to kill. There are some chemicals that will help, but this slide shows some field work, trial work that was done using a manual labour to clean the cane. For weed control, we harvested 88 tonnes per hectare. No weed control, we harvested 38 tonnes per hectare. And the equation is at the loss from lack of weed control is 0.9 of a tonne per hectare per day. Go over some 88 tonnes per hectare. Sorry about that. We can't go back. Flotation almost eliminated. Fertiliser application reduced by 30%. Herbicide application by 50%. Fuel usage cut by 47%. Tractor hours by 40%. Labour component by 66%. Eliminated use of phosphorus fertiliser for 10 years as it became available through the microbial activity. Organic matter reduced the discharges of heavy metal. Organic matter promotes beneficial fungi. Organic matter helps provide bioavailable nutrients. Sugarcane is sulphur in particular is only available to the plant after it's been broken down in the residue and picked up the following year. Macrofauna introduced and sustained. Soil biota population has positively evolved and increased. Productivity increased by 75%, and unit cost of production went down by 50%. In summary, the climate is changing faster than farmers can manage. Land managers can adjust, and we must be innovative in an approach going forward. Longer dry periods, usually broken by intense rainfall, much hotter temperatures, and in some places cooler. With higher temperatures, there is a risk of permanent wilting to crops. The technology is available, and we must use it if agriculture is to survive going forward to feed a world population. Thank you. Any questions?